Hello guys, we're gonna try making a video so I can teach you some content without having to face each other face to face. This is gonna be a video, so you can pause it whenever you need to pause it. And I'm still learning how to do this, so be patient with me. Also, when we get to the examples, I'm gonna have other videos to explain the examples. So check to see if you are able to solve those examples in the book. And if you cannot solve the examples in the book, then look at the videos that I'm going to be creating that explain step by step what's going on. And I'll do the same thing for the extra practice problems. I'll create a video for each one of them, and then just look at the ones that you need help with. Each is going to start with the answer, so if your answer is correct, move on. You don't have to watch the video, but if your answer is incorrect, look at the video to see how things are solved. So the first thing we're going to do is go here and start from this current slide. This is wait a minute, this is not the slide I need. This is the one that I need, sorry. So we stopped here. We need to get started on page 439. This is about how to draw electric fields. And that's just a representation. It's drawing the electrostatic forces. And remember, those are forces of charges that are static. So they are not moving. We had positive and negative charges. They were not moving. They exert some kind of attraction or repulsion with one another. So these are going to be these kind of forces and how they affect a positive stationary charge. That's going to be our test charge. So it's all in respect to an imaginary positive charge. Let's look at these. If you have another positive charge, you know that if you had a positive charge next to another positive charge, they don't like that. They're repulsed by one another. So those forces are to get away from one another. That's why you have your arrows pointing out. The electric field that you create is one of repulsion to try to get away from one another. They go away from a positive charge. On the other hand, if you have a negative charge, and this is in respect to the test charge that is positive, the positive and the negative are attracted to one another. So they want to move close to one another. And to represent that attraction, the electrostatic field is going to point in towards the negative charge, because that's what a positive charge would want to do, is to go closer to the negative charge, towards the negative charge. Okay, so we're going to be drawing lines. That's what we're going to be doing from now on. This should make sense to you. As we move closer to the charge, the electric field is stronger. Okay, remember that the shorter the distance, the more attraction or repulsion, the more charges that you have, the more attraction or repulsion too. Please notice too that these are straight lines. They cannot cross one another, okay? So no intersect one another when you're drawing these lines. And let's move on to the next one. Oh, here it says here that it's to help us visualize the electrostatic forces. So that's what we're doing. We're just trying to represent those forces in drawing format so we can see them. How do we draw these electric forces? Okay, the electric field lines. Figure 13.5 explains to you how to do that, but there are rules. So let's look at the first one. The relative number of electrical field lines, so how many lines are you going to be making coming out or coming in the charges that you have there, is proportional to the charge of the particle creating the field. I should say the field, not the key field. So basically, the higher the charge, the more lines you're going to be making coming out or coming in into the charge. But that's kind of relative. There is no rule about how many lines to make. You just have to represent it on your own. Rule number 2, the arrows that form the electrical field lines point out of positive charges, as we saw before, and into negative charges. Just remember that this is all relative to a positive charge, a stationary positive charge. What would it do if it was in contact with another positive charge? Try to get away from it. So those lines are coming out. When it comes close to a negative charge, it's attracted. So those lines are going to come into the negative charge because it's attracted towards that charge. And never, never, never cross those lines. Okay? That's rule number 3. Electrical field lines can never cross. So here you have a positive charge, a negative charge. As you can see, the lines are coming out of the positive. They're coming into the negative. Look at the points of the arrows. It tells you what's going on with those forces. And we don't know the charge. They didn't tell us how much each one of them was worth, but they made several of them coming in or coming out. You know that they're attracted to one another. So here they are, meeting one another in the middle. For each one that is coming in or coming out, you have to match it to another one. Okay, you cannot have just one here ending by itself. If there is one coming out, there's one that's coming into the other one. So they need to match, okay? As many as you make on one side, need to match on the other side. Here you had 2 positive charges. They're repelled by one another. So all the lines are pointing out. You see the arrows are pointing out. You can make them at the end if you want to. This person just put them right here, but you can put more than one if you want to. And here you can see the repulsion because there is no lines coming from one to the other connecting them. They're trying to get away from one another. And this is how you represent those electric fields, okay? You're going to be doing this or this depending on the kinds of particles, charged particles that you have present, those stationary particles. Example 13.3 on page 442. So right now you should be pausing and trying to work on these 2 examples. I will have a video that explains how to do that. So right now you could stop and look at the video on how to solve these 2 parts of the example 13.3, and then on your own you should be trying to do on your own on page 577 number 7, and I'll have a video on this one as well. I'll give you the answer at the beginning, and if your answer matches what I say to you, remember, I'm not being very picky about significant figures, although you should try to do the best that you can with that. If you come close to the number I give you, you can skip the video, but you can try again if you want to, or just watch my video to see how it's done. So I put in a square here, or rectangle is a type. The electrostatic force determines acceleration. So the more electrostatic force, okay, the more acceleration. And it's proportional to the density of the field lines. Remember that the electrical field, you're going to represent it by doing lines. So the more charge, the more lines you should be drawing there. So the more dense the drawing is, it has to be proportional to represent that electrostatic force, the more acceleration you have to for those particles. So keep that in mind when you're trying to solve these. So here we go. Let's keep moving with the information part of this video. Calculating the strength of the electric field. That's on page 443. So we have 2 equations that you're going to be using for the next set of problems. This equation right here gives you the instantaneous electrostatic force. So add this to your long list of equations that you're using for physics, or if you're using cards for each one of the modules, to your module card for equations, okay? And there are steps that are in the book to show you how from this equation right here you can derive this other equation right here, okay? We're going to be using both. And this one right here allows you to calculate the magnitude of the electric field. So there are two things that you can calculate, and some problems ask you to find the instantaneous electrostatic force, and some of them may ask you to only calculate the magnitude of the electric field, or maybe in the same problem you're going to have both of them to calculate. Okay, so here you go. E represents the electrical field at a given point in space. It's a vector. Remember, all of these are vectors, and your units are the Newton divided by the Coulomb. Then F of E here, this F of E, and remember, if you see arrows, because I know that your book sometimes doesn't put arrows, but that just represents that these are vectors. That's all it is. In your book, you have it bolded, but you also can represent a vector by putting a little arrow on top. So F of E is the electrostatic force experienced by a positive test charge. So it's all about that positive test charge. What would happen to that charge that's positive, okay? That is placed in the field. So you put it there in the field. What happens to it? It's a vector, and the units are the Newton. And this Q with a little 0 or O, whatever you want to call it, is the initial, remember? It's the magnitude of the positive test charge, and the units are always in coulombs when you're talking about electrical charge. If there are two or more stationary charges making up the electric field, the electrostatic force will be the vector sum of each individual charge's electrostatic force. That means that in these problems that come next, sometimes you're going to have to add vectors. And we just practiced adding vectors last time we met. You need to remember how to do that to be able to do the next set of problems. As a result, the electric field will also be the vector sum of the electric field from each individual charge. I know it's a handful of words, but once we start doing the problems, you'll see what we mean. This is a constant. If you remember that constant, usually the problems give it to you, so you don't have to remember if you don't want to. You can put it also on your list of formulas to have there if you want to, but the problems should give it to you. Okay, here we go. Next. E, remember, electrical field 1, electrical field 2 is a magnitude, so we don't use the sign of the charge in the equation. So if Q, which is the stationary charge, is positive, then the electrical field points directly away from Q. Because remember, that's positive. It's getting away from the other imaginary positive charge that you have there. Now, if your Q is negative, remember that the electrical fields are represented by arrows or lines that come into the negative charge, okay, pointing towards the Q. So in the problems you're going to be calculating electrical fields, okay? What happens? Well, those two, for example, right here, for the blue one is attracted to it. And the positive one is coming out, is also moving that one. And if you remember going to the right, if you're a vector, you're going to be positive. And if you go to the left, if you're going the other way, you're going to have negative numbers. Okay. So here we go. Let's look at the examples. On page 444, you can have your first example, 13.4. Watch the video. Okay, try to work through the example you have in the book. I know that's not the way we do it when we meet face to face. I'm going over the example with you on the board, and I'm going to be making a video on it. So you can do it that way too. You can just follow me through the video. Stop here, open the other video, and look to see how this problem is solved. You can also just work through the book, and if you're having problems, then look at my video. It's up to you, really. So let's move on. There's a second part to it, and after you have successfully understood the two examples the book gives you, please try to do the extra practice problems on page 577, number 8 and number 9, and I'll have videos on how to solve those as well. And once again, I'll give you the answer first. If your answer is very, very similar within a few significant figures. It's fine, move on. You didn't get the answer, you can try again, or just watch my video to see how it's solved. There you go. Okay. If you did chemistry with Apologia last year, you did learn about the Bohr model of the atom. This is a helium atom. Remember the helium atom, atomic number 2. That means it has 2 protons in the nucleus, meaning it also has 2 electrons. Okay. So this is for a helium atom. And because you have charges right here, okay? You can apply Coulomb's law to the Bohr model of the atom. Oh, lucky us, huh? It's gonna be a lot of fun. Here in this drawing right here, which is on figure 13.6, if it's not exactly the same drawing, it's a similar one. But remember what orbitals were. If you remember this from chemistry, if you have taken chemistry before, the Bohr model of the atom is not the model that we use today. We use a quantum mechanics model of the atom, which is more of a cloud or a zone where you can find electrons. But in this case, we pretend that electrons can be found on circular orbitals that go around the nucleus. And the farther you are from the nucleus, the more energy that electron has. So these ones are on ground state, closest, lowest level of energy, but they can jump. If you give them energy, they can jump to other orbitals, and then they'll come back down because that's what they like to do. They like to be on the lowest energy level. This is a review of chemistry. I'm just having fun with it. But anyway, you can calculate how fast the electrons orbit the nucleus. That's pretty amazing to me. So anything that goes on around and around and around, we have centripetal force. Here is your formula for centripetal force because they're going around and around. The electrostatic force, so remember, forces that come from particles that are static, okay? Or in this case, the electrons are moving, but how they influence one another. The electrostatic force is supplied by the centripetal force in here. So on page 446, you can find this figure. And then you're going to have to solve problems. The example that shows you how to use both formulas together is example 13.5. You can find that on page 447. Once again, try to follow it in the book, but I'm going to have a video on it too. So you can pause right now and look at the example on the video that says example 13.5.